In this video, I will discuss only the homework that was given in the previous lecture. We had 16 distinguishable particles and they were having 16 epsilon energy in total. Now the three possible macro states that were supplied in the given problem were these three. Many macro states are possible. For this set, we have 16 distinguishable particles. They are carrying total energy 16 epsilon and each quantum level is differing by 1 unit of energy, that is 1 epsilon. So we can design many complexons, that is macro states, but only 3 macro states were given in the problem, 1, 2 and 3. Now see, this is 0, this is epsilon, this is 2 epsilon as shown here. So we have 16 dots representing 16 distinguishable particles. So 16 into 1 epsilon equal to 16 epsilon. So it is satisfying the total energy. Now here, what will be the thermodynamic probability? It will be 1. Since the internal arrangement can be ignored and has no relevance, all these 16 particles are accumulating in this first excited state. So there is only one possible arrangement for this macro state. So this will carry only a single microstate. This macro state will be associated only with a single microstate. So it will be 1. Now if we use the formula, it will be 16 factorial upon, it will be 0 factorial for the first level, that is the ground state, then 16 factorial and so on. For the next level, it will be 0 factorial and so on. So this will cancel out and it will give us 1. So only one microstate will be available for this macrostate. Now we switch to the next macrostate where we have 4 particles in the ground state. So it will be 4 into 0. Here we have 8 particles, 8 into epsilon, and here we have 4 particles. So 4 into 2 epsilon. So here it is 8 epsilon and 8 epsilon. So total is 16. So energy is matching. So this is a possible macrostate and the number of microstate for this macrostate can be determined using the formula. It will be 16 factorial by, here we have 4 factorial, here we have 8 factorial, again 4 factorial, and then we have 0 factorial and so on. So we have 16 into 15 into 14 into 13 into 12 into 11 into 10 into 9 into 8 factorial. And here it is 4 into 3 into 2, it is 8 factorial, and we have 4 into 3 into 2, and this will cancel. Now if we perform the calculation, we will have 900. So it will be almost equal to 9.0 into 1, 2, 3, 4, 5, 10 to the power 5. So nearly 9 lakh microstates will be available for this macrostate. So it will be impossible for us to determine marking A, B, C, D, E, F, G, H as I have discussed in the previous lecture to find the possible number of microstates. We have to use this formula. Otherwise, it will be an unsolvable problem. So this is for the first macrostate, this one, 1. This is for the second case, it is 2. And for the third macrostate, what we have? We have 7 particles in the ground state, 4 in the first excited state, 3 in the second, and 2 in the third excited state. And thereafter, there is no particles. So the number of microstate in the third macrostate, that is the thermodynamic probability corresponding to the third macrostate is, it will be 16 factorial upon, here it is 7 factorial, then 4 factorial, 3 factorial, 2 factorial. So 7 plus 4, 11, 11 plus 3, 14, plus 2, 16. And to find the energy, we will multiply this by 3 and this by 2. So it will be 6, 6. 6 plus 6 equal to 12. And 12 and 4 is 16. And here these particles have energy 0. So here we write 16 into 15 into. This is for the 4 factorial, this is for 3 factorial. Now here also 7 factorial, 7 factorial will cancel out, and solving this we will get. So thermodynamic probability is almost equal to 1.44 into 1, 2, 3, 4, 5, 6, 7 into 10 to the power 7. Near about 1.5 crore microstates for this macrostate. Now this is the problem of having the number of microstates with only 16 particles and 16 epsilon amount of energy. Now think about the figure that will be obtained when we will deal with the actual system. In an actual system, there will be an assembly of infinite number of particles of the order of Avogadro. So there will be 10 to the power 23 number of particles, and the number of levels that will be occupied will also be in huge number. So you can easily guess the figure that is going to come out for any possible macrostate. That will be monumental. So for a real system, in which we will have number of particles in the order of Avogadro number and having a large number of levels, and those particles will occupy all those levels and they are distinguishable. So what will happen? We are going to have a monumental figure for the number of microstates, that is thermodynamic probability for a corresponding macrostate. The homework that was given is that we have two systems, A and B. A was at a higher temperature T1, B was the cold body, and it was having one particle having energy 3 epsilon, and system B was carrying 3 particles having energy 1 epsilon. Now these two bodies were brought in contact with each other. and the composite system was isolated from the surrounding. Now we have 4 distinguishable particles with 4 epsilon energy in total. Our task that was given in the homework is to find the direction of the flow of heat. Now we all know that heat flows from hot body to cold body spontaneously. We have studied it in thermodynamics. Now we have to prove, as per the instruction given in the problem, using the concept of probability, that heat flows from A to B. Now for this, let us first analyze the conditions that was prevailing within these two systems. So system A has one particle having 3 epsilon energy, means it was residing in this level. Then only it can carry 3 epsilon energy, 3 units of energy. This was system A. And system B has 3 particles. Now here we have A. Let us name these 3 particles that is in system B to be B, C and D. Now these 3 particles are sharing energy epsilon in total. They are carrying 1 unit of energy. 3 possible arrangements can be obtained for this system. We have B here and C and D here. We have C here, B and D here, and D here, and B and C in the ground state, so that the energy will be 1 plus 0, so it will be epsilon. So it has 1 possible arrangement and it has 3 possible arrangements. Now when these two systems are brought together, then we have 4 distinguishable particles having total energy 4 epsilon. Now that system was actually the problem that was discussed in the previous lecture, that is 4 distinguishable oscillators having total energy 4 epsilon and to be distributed among energy levels separated by 1 unit of energy, that is epsilon. So we have the composite system ready. Now to prove that energy will flow from the hot body to the cold body, that is in this direction spontaneously, we have to prove that the probability of enjoying energy levels by A greater than 3 epsilon will be less in the composite system compared to this one, and the probability of enjoying lower levels compared to 3 epsilon in the composite system will be higher. So in the composite system, this will come down in maximum number of microstates than going up. So that will prove that it is losing energy and these particles are gaining it. So let us just find the probabilities. For this, we will take the composite system and we will count the number of microstates having A greater than 3 epsilon in energy and having A in those levels with energy less than 3 epsilon. Here it is having lower energy, so we count this microstate. We will use this token and so we get 1 microstate having lower energy. Now we come to macrostate 2. Here we see one microstate having energy greater than 3 epsilon. This is this is 0 epsilon, 2 epsilon, 3 epsilon, and this is 4 epsilon. So higher probability we are getting 1. Let us write here. This is the higher energy and this is low energy compared to 3 epsilon. Now in the remaining 3 cases we have A to be lower. So we count this. Now we come to macrostate 3. This is 0 epsilon, 2 epsilon, 3 epsilon. Now it is not coming to 3 and 4. It is 2, 2, 0, 0. So all these microstates will be counted. We have 6 such microstates. Number of microstates equal to 6, in which A will carry lower energy compared to 3 epsilon. Now come to macrostate 4. In macrostate 4, it is 3, 1, 0, 0. Now we will ignore the microstates in which A will reside in energy level 3, because we are considering only the lower energy levels and higher energy levels which is getting occupied by the particle A. So these 3 microstates will be ignored, 1, 2 and 3. Here A is enjoying 3 epsilon. But in all the remaining microstates, which is 9 in number, it is total 12. So 3 is getting ignored. So 9 will be left. In all those 9 microstates, we will have lower probability. Now, this is the last macrostate for the composite system, and again we see it is not going to either 3 or 4. So here in all these cases A will occupy the lower energy. So we have to count all these microstates. We have 12 microstates in macrostate 5 as described in the previous lecture. So it is 6 plus 3, 9, 9 plus 9, 18, 18 plus 12, 30, 31. And we have higher energy to be 1 only. And we have ignored 3 microstates where A was enjoying 3 epsilon. So in total we have 31 plus 1, 32 and plus 3, 35. So these are the total number of microstates that we have obtained, and it is possible for the composite system. Now what is the probability of this low energy for A? So probability for low energy of A in the composite system is 31 by 35. And the probability for higher energy of A in the composite system is 1 by 35. And the probability of having similar energy is 3 by 35. Now you see that the probability for A to enjoy low energy than the previous case is much greater than the probability for having higher energy. So what we can predict is that this is getting down. So it is losing energy, and this energy is being shared among these particles. Now if we judge the other particles, we will find that B, C, D will occupy the higher energy levels more. So here you see that 2 particles are always in the ground state, but if you visit these microstates, you will see that here you have 2 particles in the higher energy state, and if you study all these, you see 3 particles in the high energy state. So these particles will gain the energy that is being lost by this high temperature body, hot body, and they will enjoy higher levels. So we can say from this probability judgment, considering thermodynamic probability, that heat flows from hot body to cold body spontaneously.